Swayam Prabha. Digital India. Educated India.
Good morning. Once again, you are all welcome to this lecture, Soil Mechanics, Geotechnical Engineering 1, and we have completed quite a few topics, and just now we have completed the shear strength topic, and this is a very important topic of BSD. And now we are going to start a new topic, that is your compressibility of soils. And compressibility means what? Compressibility means under loading the volume change, and in fact and that volume change, if that volume change actually it can be in all direction, but in soil actually what we will see ultimately we want to see the vertical compression, though it will be there in all direction. The compared to other direction, vertical compression will be larger, so that we will try to address. And in fact, when a material is loaded, generally it will have change in volume or length or dimension. And in solid mechanics, we have learned that when a rod is applied by axial load, then based on its compressive or tensile, it will be elongated or shortened. So, here also in soil, if we apply the this type of compressive load, generally soil will we apply compressive load. So, generally it will be there will be a compression, and that will be there because of this some sort of elastic nature of soil. And in addition to that, in soil mechanics we will experience some other sort of compressibility or shortening or compression, that is because of another phenomena called consolidation. And this consolidation cannot it is not a phenomena for all types of soil. This is generally is a phenomenon for fine grain soil, and particularly when fine grain soil is saturated and we apply load, then this consolidation generally take place. So, exact mechanism of consolidation we will discuss later part to estimate the rate of consolidation, etc. That time I will elaborately discuss that mechanism of consolidation. Right now, we are considering the just compression because of the reduction in void ratio. And as introduction, what I can say, the effect occurs of saturated fine. So, that means consolidation is the for saturated fine grain soil it happens, and a large wheel load rolling along a roadway resting on a clay wheel cause an immediate settlement which is recoverable once the wheel is passed. That means, we have actually that elastic whatever I have mentioned, that on the road, suppose if there is a load applied through wheel or anything, then we will see initially there will be a depression, but when you will pass, then it will be again coming back to the same position, that is actually elastic compression. But this consolidation settlement is not recoverable, and it will do with time. So, that means so that is the if the load same load like it is passing, then it is recovering, but if the load is continuously kept here for a longer period, then permanent there will be, in addition there will be a consolidation settlement. And this consolidation settlement actually that means we have if there is a settlement in foundation, suppose if there is a foundation here and you have constructed over here, then load is applied through this. Over the time, this settlement, this foundation will settle by some amount. We will see some will go downward. This amount of settlement is S. This S will be combination of three component actually. Right now, I will not discuss third component. Basically, I will discuss first two component, that is one is elastic, another is consolidation. And so, soil when loaded, the elastically it will also settle, and in addition to that, if there is a fine grain soil saturated, then immediately after loading within the soil there will be development of pore pressure, and slowly that pore pressure will be dissipated, and slowly because of the dissipation of pore water pressure, the load, actual load will be slowly transferred to the soil grain, and that because of that loading soil grain will try to come closer, and that will result the reduction in void ratio, and that will be finally result in the final compression. So, reduction in void ratio basically will happen because of this consolidation process. And now, this one typically further this mechanism of consolidation etcetera we will discuss later on, when we will try to address the issues of rate of consolidation, that how long it will take. Suppose I know a particular foundation will undergo this much amount of consolidation settlement, but my second question will be how long it will take to complete the consolidation settlement. So, that time I later part of this topic of this lecture I will discuss. Right now I just mention just want to highlight that there will be consolidation settlement, and this consolidation settlement will be this consolidation settlement will be can be estimated or can be based on the observation actual foundation how much is the settlement we can find out, but it is very difficult to differentiate what is the consolidation settlement, what is how much is the consolidation settlement and how much is the elastic settlement. So, to assess that we have different theories also, we can estimate by calculation how much will be the elastic settlement, and also by consolidation theory I can find out how much will be the consolidation settlement. And this actually in the laboratory also we generally try to understand the compressibility behavior of the soil, we carry out test in the laboratory, and one such test is called odometer test. And this odometer test if I see this is the type of sample we keep here, the sample is here, and this is the porous stone at top and bottom, and this is actually odometer actually where we put the sample, and this sample entire sample will be immersed in water, so that it will be saturated, and then through this cover we apply the load through here, and if we apply the load, then as we because of this loading the soil the load will be finally since transferred to the soil through this mechanism. The when soil, that means this is a saturated soil and we have applied now the load, and when this if it happens, this is all void spaces are filled up with water, and then when this load is applied, the immediately after this loading application of this loading, this load will not go to the directly to the soil grain. What will happen? Because of this incompressible nature of the incompressible nature of this water, this water will be getting pressurized and in the form of excess pore pressure, and when excess pore pressure will develop, then that excess pore pressure cannot stay longer. So, it will try to dissipate, and how it dissipate? When through seepage of water through the porous stones. So, that means, when you apply a certain amount of load, then the excess pore pressure will develop, and this excess pore pressure will be dissipated because by the seeping of water through this porous stone. So, like that when because of this application of the load, whatever amount of excess pore pressure develop, and if this load is kept for a longer time, then slowly water will dissipate, and finally, this pore water pressure will become 0. And when this pore water pressure becomes 0, that time entire load whatever applied externally, that will be transferred to the soil grain, and that will cause the soil grain to come closer, and that way actually it will be volume change will be there. That volume change in other direction restricted, we can assume that is a one dimensional, then vertical compression will be there. So, like that. So, if you laboratory if you do this this soil, and if we apply a consolidation here, another important thing is if I apply load P 1, under this load P 1 there could be end of consolidation, So, suppose you have applied load P 1 and the sample compression versus time, if you plot, at some time it will be, suppose under pore pressure becomes 0. So, under P 1 this much is the consolidation settlement, but it is not that further compression of the sample is not possible. Now, if I apply another load which is magnitude P 2 now. So, if I apply further another load P 2, then compression will start from here, and under this load there will be another amount of compression, and which is equal to this. So, like that, so each under application of each load, after application of each load there will be compression, and so that means when we apply particular load, with respect to that load we have the consolidation. So, when you talk about consolidation, you have to mention, it is necessary or it is essential to mention under what pressure. So, if I apply pressure P 1, it will have some amount of consolidation. If I apply load P 2, then the consolidation will be something else. So, like that, if you continuously change, and you will get the different pressure loading, different consolidation. But here actually you can see, when there will be a virgin soil, if you collect, and initially you apply a small amount of P 1, and under that there will be compression, but when under first loading compression takes place, if I increase the second equal amount of load, then magnitude of compression in the second stage will be smaller. Obviously, the soil already become compact, and so the later stage, to get the certain amount of consolidation settlement, we need much higher load. So, though this diagram does not properly in scale, but this magnitude towards end under same loading, suppose if P 1, P 2, P 3 all are equal, then this magnitude will be reduced. So, this is one sort of that means, if I apply load, and because of this consolidation mechanism there will be compression, and that compression actually we need to estimate, and to estimate this we can introduce some terminology, and if I estimate those parameter, and then we can find out the settlement. So, for that let us go to the next slide, and you can see as I have mentioned that under each loading, suppose you have applied load P 1, and then under load P 1, and suppose before loading P 1 the void ratio was before there is no suppose it is load P 0 and that time it was E 0. Now, if P 1 is applied, then and that is kept for some time, that it will be compressed, and when you see that suppose after 10 days or after 2 days or after 1 day, initially the rate of settlement or compression is quite high, and towards end it will be decreased, and over a long period of time, if you see there is no decrease or the decrease is very negligible, without measuring pore pressure, I can declare that the consolidation is completed, and under that condition, if I measure or if we estimate the void ratio, suppose this is E 1. Similarly, under load P 2, and like that at the end when there is no change of thickness, then if I estimate the void ratio, suppose E 2. Obviously, the whatever void ratio was here initially, the E 0 will be greater than E 1, and again it will be also greater than E 2, like that. So, if I increase load continuously, that means your void ratio will be decreasing, then only voids the decrease of voids will be the resulting in the compression. So, that is what finally, for different loading, suppose P 1, P 2 like that, in number of loading, if I find out void ratio and finally plot in a E versus P plot, if I do, then typically we get a curve like this E P curve. and suppose this is the one, suppose P pressure P or P, corresponding void ratio P1, P2 corresponding void ratio is E2. Like that I can draw a curve. Suppose while doing this, developing this curve, we apply pressure 100, 200, 300 or 400, like that. There is a certain ways we have to do. But now if I want to find out void ratio at some other pressure, that means suppose 150, then from this curve, suppose this is 100 and this is 200, 150 is middle. So, I will just produce here and from there I will read the void ratio. So, that is the way actually we can find out void ratio. And typically during consolidation, again you can see that you have applied certain amount of load here, and then after loading this void ratio, like the similar one, this is going up to this point, and sometime if you remove the load, then again it will be some sort of expansion will be there, and it will go in some, it will not go back in the same rope path, it will be rebound in this way, and it will not go to 0, it will have some permanent compression. And then if you apply further load from here, it will again at certain path will follow and compress, and when it reach here and in further increase of pressure, again this curve and this curve, it will continue further similar, it will be become continuous. So, up to the here, if you remove the load, it will go this way, and if you further loading, then it will come back at this point, and again it continued is the same continuous line, a curve. Now, if you want to estimate the amount of compression, then we use a term, that is coefficient of volume compressibility, and this what is the definition actually? The volume change per unit of original volume constitute the volumetric change. Okay. So, volume change per unit of original volume is a volumetric change. If a mass of soil of volume V1 is compressed to a volume V2, that means original volume was V1 and final volume is V2, the assumption is made that the change in volume is caused by the ratio. That is the thing already I have mentioned, that if this is the original initial volume, and then final volume is this, and this is the volume change is there. This volume change only because of the change in void ratio in this mass, soil mass. So, that if that is the assumption is made, that volumetric change is V1 minus V2 by V1, and then V1 actually you can say if I V1 can be written as V naught into 1 plus E1, like that V2 also can be written as or V1 actually that way you can apply V naught into 1 plus E1, V naught into 1 plus E2 and V1. So, like that if I express in terms of void ratio corresponding volume, then you can this V1 will become this, and obviously you can assume that V naught is added here, it get cancelled finally. So, ultimately 1 plus E1 minus 1 plus E2 by 1 plus E1. So, volumetric change which was delta V by V1. What is delta V? The original volume minus final volume by V1, and if I express this way, then ultimately this become E1 minus E2 by 1 plus E1 sorry E1 minus E2 divided by 1 plus E1. So, 1 plus E1 I can consider as the original volume, and this almost become the change in volume, where E1 is the void ratio at pressure P1 and E2 is the void ratio at P2, and E1 obviously higher than E2. And then MV defined as a volumetric change per unit pressure, sorry. Volumetric change per unit pressure, that is MV. If H1 is the original thickness and H2 is the final thickness, the volumetric change this way we can write, also I can write in this way, because area if it is constant. So, V 1 actually A into H 1 and here also A into H 2, because cross section area if you see consider same, and then this one also can be expressed in this way, and this is again equal to this previously this one we have shown that this is the one expression. And again if I E versus P, the slope of the E versus P curve, that is called A. So, del E by del P if I define as a term as A, and then volumetric change will become A dP by 1 plus E. So, if the combining these, so your volumetric change become your A dP by, because 1 minus E minus 1 minus E equal to A dP if I multiply. So, this become E times this become A times dP and divide by 1 plus E. So, that is the thing we have shown here, volumetric change A dP by 1 plus E 1, and so and MV definition is volumetric change per unit pressure increase. So, A dP by 1 plus E 1 divided by dP. So, dP get cancelled. So, A by 1 plus E 1. So, A by what is A? A is the slope of E log P curve. How to find out the slope? If I P 1 here, P 2 here, then I can find out what is the P 1 P 2 and what is A 1 A 2. So, that slope will be your A, and 1 plus E 1 is the you can nothing but is the original volume. So, that is M V equal to this A by 1 plus E 1. And for most soil, most practical engineering problem, MV values can be calculated for pressure increment of 100 kN per meter square in excess of the present overburden pressure. Suppose that means in a soil at point, what is the effective overburden pressure at present? Above more than 100 in excess, that means if it is 200. So, I can find out MV for 300 kPa pressure. And that can be used for calculation. Once the coefficient of volume decrease has been obtained, we know the compression per unit thickness per unit pressure is the increase per unit pressure increase. That means compression, total compression can be obtained delta C equal to MV by definition. If I multiply it by dP and if I multiply it by thickness, then it will be your total settlement of the. Suppose if there is a layer here of thickness H and M value of MV here to obtain, and then and your pressure increase, original pressure was something, and because of some loading you have increased the pressure equal to delta P, then your settlement will be MV dP into H. So, this is one way to find out the compression, that is called MV approach. That means, by using coefficient of volume compressibility, one can find out the compression of the soil or settlement of the soil, consolidation settlement of the soil. Now, typical values of MV for different soil obviously will have different MV values. You can see peat has this much very high, and plastic clay will have this much comparatively less, steep clay will have further less, hard clay will be further. So, that means the organic clay will have maximum compression, plastic clay will have intermediate, and these are the soil where we will have lesser compression. That means, MV value based on the value of MV we can assess the which one will undergo more compression and which one will undergo lesser compression. So, this is the typical values, but this value not necessarily you have to remember, you can estimate in the laboratory and for each soil, because these are actually a range is given, because 10 to 2 is a very high range. So, for use in calculation you need to find out in the laboratory. And now, this one I can show with the help of a application. That means, whatever we have application of volume compressibility, I can show through this example. and you can see the tabulated results were obtained from a consolidation test. That means, whatever table I have given here, that is when 0 pressure, the thickness of the sample was 20 millimeter suppose, and then when you apply 50 kPa pressure, then the original thickness 20 millimeter become 19.65 millimeter. So, it is compressed. Then when you applied 100 kPa pressure, then it is to 19.52. When it made 200, it become 19.35, and you can see when it become 400, it become 19.15. When it become 800, it become 18.95, and then at the end, when after reaching to this pressure, we can remove all the load, and then you allow to expand, and finally full expansion, and we have seen the final thickness is 19.25 millimeter. So, this is the data actually from the laboratory. This thickness is at the end of the consolidation of 50 kPa pressure, at the end of consolidation of 100 kPa pressure, like that it is given. So, each pressure increment having been maintained 24 hours, and after it had expanded for 24 hours, the samples were actually it should be were removed from the apparatus and found to have moisture content of 25%. The particle specific gravity of the soil was 2.65. Plot void ratio to effective pressure curve and determine the value of the coefficient of volume change for a pressure range of 250 to 350. So, coefficient of volume change when you talk about, then you have to always mention the pressure range, because with the change of pressure, coefficient of volume change will be changing, because it is volumetric change per unit pressure change. So, because of that, what range of pressure you need this, that has to be specified. So, if I see now this problem, there are 2-3 methods actually can do, and one method I will just first explain, that is actually from the end actually can start, and solution is, since at the end of the consolidation, when after removal of the load, when it is fully expanded, at that condition also soil will be saturated, and water content was measured 20.25% and G was 2.65. And so, we know that saturated condition S into E, W into G, and S equal to 1 at saturated condition. So, E become W into G. So, we can find out E equal to W G. So, that means equal to 0.662. That means, at the end finally after expansion, whatever void ratio was 0.662. So, this void ratio corresponding to a sample thickness of 19.25, that is one table you can see that 19.25 thickness at the end. So, the corresponding to that thickness we have void ratio is 0.662. Now, we know that dH by H1 will be equal to dE by 1 plus change of void ratio divided by original void ratio, total volume here. So, dE become 1 plus E1 by H1 into dH, and if I put original void ratio is 1 plus E1 become 1.662 and H1 is 19.35. So, last we are starting from the end actually, and it is dH. So, your dE we can calculate from here, that based on this, dE actually equal to 0.0865 dH. Okay. So, if this is the one, and then I can go back to this one, you can see 19.25 and thickness and void ratio this one, and we have got D equal to 0.0865, D equal to 0.0865 dH. So, we know this is the thickness and this is the corresponding void ratio, and we have got change in void ratio in terms of thickness, we have got this. So, now for this what I will do, this minus this I will do. So, this thickness minus this thickness, if I do, you can see it is minus 0.3. So, that means dH is minus 0.3. So, the dE will be equal to 0.0865 multiplied by minus 0.3, and that gives you minus 0.026. So, what is the void ratio will be here? So, this plus this. So, that means if I do plus, then it will become ultimately, since it is a negative. So, it become 636. Okay. And similarly, I will do now this minus this, then the dH become this and dE become this, and this if I add, then it void ratio become this. Similarly, I will do this minus this, then I will change in thickness will be this, and if I use this equation, then dE become this, and then your E become with respect to this plus this plus this, so you can see become 0.671. Similarly, if I do this minus this, and then your change in thickness become this, if I use this equation, then your D become this, and what will be the final void ratio? This plus this. So, this one. Similarly, this minus this, if I do, I will get the dH is this, use this equation, you will get dE here, and what will be the final E? So, this plus this become this. So, this is the way one can calculate the void ratio corresponding to each pressure. So, 0 pressure, what is the void ratio? 50 pressure, what is the void ratio? 100, what is the void ratio? 400, what is the void ratio? Now, we have got pressure corresponding to each pressure, we have got the void ratio. Now, we can plot the EP curve, and after drawing the EP curve, we can find out the slope of the EP curve A, or A by 1 plus E is the MV, and what range actually you have to find out the slope between 250 to 350. So, we will do that one in the maybe in my next lecture. Maybe I will stop here. I will continue maybe rest of the calculation in my next lecture. Thank you.